I've been curious about the natural world since I was a very small child growing up along the shores of the Chesapeake Bay, where I very quickly learned to study all the different animals and pick up trash, which led me to study marine science and oceanography in school. And during my studies, I learned that the ocean was in a great deal of trouble from human impacts, from overfishing, from pollution, as well as climate change. And I wanted to do something about that. And for me, doing something meant using science and technology to find novel ways to keep track of what was happening in the ocean and look for solutions. Coral reefs are valued at billions of dollars across the world for fisheries, sustenance fisheries in island nations.
Tourism and new compounds for the pharmaceutical industry are two examples of how coral reefs have contributed a lot of money and generated wealth for a lot of people. We have this tremendous wealth of different types of ecosystems and species on this planet, and having these reefs around to maintain a sort of biological stock of genetic uniqueness is really important for genetic diversity, ecosystem health, and resilience of the ecosystem in the face of things like climate change and other sort of stresses they may encounter in the future.
They've been called the canary in the coal mine. They're one of the first marine ecosystems to start to show very significant degradation from ocean temperatures increasing and ocean acidification. And there simply aren't enough people that can be scuba diving in the water all the time to tell you how the coral reefs are doing. So we need new ways to monitor them using things like satellite imagery that can easily cover all parts of the world, even in places that you can't very readily get a person to. What the ER2 is doing is telling us what coral reefs would look like from space.
I'm an environmental scientist. I study ecosystems. I study how those ecosystems are impacted by external pressures such as climate and population. Our part in this project is to understand the color of coral reef signatures coming out of the water. What colors will the High-Speary sensor see? Live corals look very different from dead algae-encrusted corals, and they look very different from the surrounding uncolonized sand and coral rubble. So by looking at the detailed spectrum of light coming out of the water in the visible and near-infrared portion of the spectrum, we believe we'll be able to say something about where the coral resides and how healthy it is. In order to interpret the data that's being collected by the ER2, you have to know something about the inherent reflectance of the features in the ocean floor that we're interested in. Healthy coral, not healthy coral, bare sand, and rubble. So what we're doing is we're measuring in water the reflectance of the ocean floor very close to the ocean floor. But also we're deploying radiometers at the ocean surface so that we can understand the change in that color as it propagates through the water column to the surface. That's the information that needs to be taken into consideration when we try to interpret the data in terms of coral health. We have to essentially remove the effects of water.
This is something relatively new, using satellite imagery, using hyperspectral imagery to categorize coral reefs. We're collecting bottom spectra underwater of coral, algae, and sand so that we can better use the hyperspectral imagery to figure out how much coral and algae or sand there are in each specific shot. It's not immediately obvious in a satellite image whether a pixel is coral or algae and how much coral is in it. And to do that really well, we need to collect both pieces of information at the same time. We need an airborne image, and we also need to know exactly what's going on in the water. We can be collecting in-water data to match up with those specific images. And so we know that in a particular pixel, there's a certain amount of coral, a certain amount of algae. It better informs us how, in the future, we can remove the atmosphere and the water effects from the satellite data.
Call this coconut more. Is that? We got it inside. Okay. Our autonomous kayak system is a fully autonomous platform that's customizable, configurable, and made entirely with off-the-shelf components. It will be towing an optical sled from the U.S. Naval Research Laboratory, and we'll also have it towing a YSI XO2 water quality parameter monitoring sonde, which gives us the ability to measure chlorophyll A, fluorescent dissolved organic matter, pH, temperature, and salinity.
These sensors are providing timely and volume of data necessary to understand not only coral reef ecosystems, but all the other kinds of ecosystems around the world, in the ocean and on land,